My name is Jonathan Martin. Welcome to a short presentation on the Personal Climate Control Project. Source code, detailed parts lists, schematics, and documentation can be found at the project webpage on GitHub. The basic concept is to use chilled or heated water pumped through a cooling shirt to make the user comfortable when other forms of climate control are unavailable. This is accomplished by using thermoelectric coolers, or TECs, that can provide both heating and cooling. Similar concepts for cooling: pump pre-chilled water from an insulated cooler or use refrigeration to chill water. Heating vests typically use resistive heaters. TECs were chosen for this project because they can provide both heating and cooling and have a small footprint. The challenge of using them is that they aren't as efficient as dedicated heating and cooling systems. They do allow for one system that can be used year-round. The cooling shirt used is a commercially available shirt from Cool Shirt Systems. It is basically a cotton t-shirt with about 15 meters of flexible tubing sewn in. In the next iteration, a vest version that can be more easily used with a jacket will be selected, as well as quick-release valved connections that will allow connecting and disconnecting the shirt with minimal loss of water. The full system requires more than just TECs and a cooling shirt. Pumps are needed to circulate the temperature-conditioned fluid. Flow meters keep track of how well the pumps are working. Dual H bridges provide power to the TECs. A radiator and DC fans dissipate heat. Thermistors monitor the hot side and cold side temperatures of the TECs. A Bluetooth module allows for the system to be controlled from an app. A DC regulator provides 5-volt power, and an mbed microcontroller ties everything together. Lower power dual H bridges are used to drive the pumps and radiator fans. These are rated at up to 2 amps per channel. The TECs used are TEC 1-12706 models that are rated to draw up to 6 amps at 12 volts. The dual H bridges that drive these must be matched to safely drive that amperage. The ones selected are rating up to 7 amps per channel. Despite the rating of the TECs, the observed total power draw is only about 15 amps at 12 volts, or somewhere around 3 amps per TEC. The eventual goal is to have a system that can be hooked up to 12-volt power on a motorcycle. For the prototype, we are using a 30-amp 12-volt DC power supply connected via an SCA connector, which is a common power connection on motorcycles. This also defines our power limit. We can easily draw 20 amp from the motorcycle, but much beyond that could be an issue. Motorcycle stators don't generate as much current as car alternators. Plus, even at 20 amps, we need thick gauge power cables. If you attempt your own version of this project, then for safety, you should always use a fuse that is properly matched to the power cables you are using. It is better to blow a fuse than melt a cable, or worse, start a fire. The user interfaces with the system through a Bluetooth connected app on their phone. For this prototype, we are using Bluefruit Connect from Adafruit. The goal temperature can be increased or decreased, and the user selected state can be set. The system functions as a state machine that has a user selected state that includes off, cool, heat, and running only the pumps. Running only the pumps can be useful for filling the water loops and bleeding air from the system. There are also several internal system states, such as pre-cool and run-cool. In the event of overheating or a pump failure, the system will shut off automatically. The plotter screen of the Bluefruit Connect app shows the temperatures of the radiator and shirt water blocks over time. An LCD screen displays state information, temperature, and flow rates. These are mainly useful for debugging and aren't of much interest to a user. A PC can also be connected via USB to get real-time temperature reports over a serial connection. The system performs well, able to cool reliably down below 18 degrees Celsius under load. Heating to any reasonable temperature wasn't an issue, though before the system is seriously used to heat, it would need to be redesigned to accommodate some form of antifreeze. That would involve selecting pumps and radiators that would be non-reactive to whatever coolant was selected. The TECs will be upgraded in the next iteration with the goal of cooling closer to 10 degrees Celsius and using more of the available power budget. Better pumps and integrated reservoirs will also be added. The pumps used in this version are cheap aquarium pumps that are barely up to the task of moving water through so much tubing on the shirt water loop. They function well at moving water through the comparatively shorter and less restricted radiator loop. I thank you for your time. If you watched this far, check out the demonstration video linked on the webpage and feel free to send any questions or comments.